we will discuss implicit differentiation, the mean-value theorem for differentiation, and Rolle's theorem. Let us first consider an equation containing two variables x and y. For example, the two equations shown on the screen. Here, we consider the first equation from the previous screen, which is the equation shown on the current screen. We can solve for y as shown on the screen. This screen illustrates that the variable y we solved for previously can be defined as a function, y equals f of x, as shown on the screen. This means that y can be considered a function of x. In other words, this equation implicitly defines the variable y as a function of x. Next, let us consider this second equation on the screen. It is quite obvious that it is very difficult to directly solve for the variable y to obtain the function f of x. Although it is difficult to solve for the variable y, we can still say that this equation implicitly defines the variable y as a function of x. In other words, for any equation containing the variables x and y, regardless of whether the variable y can be easily solved for or not, we can always say that the equation implicitly defines the variable y as a function of x. Now we return to the first equation, where we can solve for the variable y, as shown on the third line of the screen. At this point, we can differentiate it to calculate dy dx, that is, to calculate f prime of x, as shown on the last line of the screen. When we consider the second equation as shown on the screen because we have difficulty solving for the variable y, we are unable to differentiate it. The so-called implicit differentiation method allows us to perform differentiation and calculate dy dx, that is, f prime of x, without the need to solve for the variable y. We consider the first equation, as shown on the screen. We can differentiate both sides of the equation with respect to the variable x, as shown on the last line of the screen. The second line on the screen is obtained by differentiating the last line of the previous screen with respect to the variable x. The two terms inside the parentheses at the beginning of the second line come from differentiating 3x cubed y with respect to x. The calculation requires the product rule, treating 3x cubed y as the derivative of the product of two functions of x. The first function is 3x cubed, and the second function is y. Please remember, as explained earlier, y is a function of x, meaning that y must be considered as a function y of x. Therefore, y is not a constant. The mnemonic rule for the product rule is: first differentiate one term, and then add the derivative of the other term. So, if we first differentiate y, we get dy dx times 3x cubed. Then, adding the derivative of 3x cubed, we get 9x squared times y. This gives us the sum of the two terms inside the parentheses on the screen. Next, we are left with the derivative of negative 4y minus 2x plus 1 with respect to x. Since y is a function of x, the derivative of negative 4y is negative 4 dy dx. And the derivative of negative 2x plus 1 is simply negative 2. This completely yields the mathematical expression on the second line of the screen. Finally, by solving for dy dx, we obtain the implicit differentiation in the last line. The answer shown on the last line of the previous screen still contains the variable y, which looks different from the answer obtained by solving for y before differentiating. In fact, these two answers are identical because if you simply substitute the previously solved y directly into the y on the last line of the previous screen, you'll get the exact same answer. This example requires us to use implicit differentiation to calculate dy dx. We will differentiate both sides of the equation with respect to x. First, let us differentiate the left side of the equation. The first term, 2xy, must use the product rule, treating 2xy as the derivative of the product of two functions of x. The first function is 2x, and the second function is y. The mnemonic rule for the product rule is first differentiate one term and then add the derivative of the other term. So, if we first differentiate y, we get dy dx times 2x. Then, adding the derivative of 2x, we get 2 times y. This gives us the sum of the two terms inside the parentheses on the fourth line of the screen. Next, we are left with the derivative of negative y cubed plus 1 with respect to x. Since y is a function of x, the derivative of negative y cubed must use the chain rule, which gives us negative 3y squared dy dx. Then, we differentiate the right side of the equation. By the same token, considering y as a function of x yields the complete mathematical expression on the fourth line of the screen. Finally, by solving for dy dx, we obtain the implicit differentiation in the last line. This example requires us to calculate an implicit differentiation involving trigonometric functions. As shown on the third line of the screen, we will differentiate both sides of the equation with respect to x. First, differentiating the left side of the equation requires us to apply the chain rule. We first differentiate the cosine function, which gives us negative sign, and then we differentiate the function inside the cosine, x minus y, yielding the left side of the equation on the fourth line. Next, we differentiate the right side of the equation, where we must apply the product rule, and the mnemonic rule is first differentiate one term and then add the derivative of the other term. Differentiating y first gives us dy dx, which is the first term on the right side of the equation. Then, adding the derivative of 2x plus 1 squared and applying the chain rule yields the second term on the right side of the equation. Finally, by solving for dy dx, we obtain the implicit differentiation in the last line. The equation on the first line of the screen can be graphed as a curve. The purpose of this example is to find the slope of the tangent line passing through the point 2, -1 on the curve. As explained previously, the derivative f prime of x represents the slope of the tangent line passing through the point x, f of x. Therefore, this example is to calculate the derivative of the function when x equals 2. Since the equation in this example implicitly defines the function y equals f of x, we are looking to calculate f prime of 2. We will use the implicit differentiation method to calculate dy dx, that is, f prime of x. We first differentiate both sides of the equation with respect to x, as shown on the third line of the screen. After the calculation, we obtain the last line on the screen. By further solving for dy dx, we obtain the implicit differentiation on the second line of the screen. The variable y in this mathematical expression can be regarded as the function f of x, as shown on the last line of the screen. To calculate the slope of the tangent line at the point 2, -1, we consider that when x equals 2, its function value f of 2, which is the y value, is equal to -1, as shown on the first line of the screen. Therefore, the slope is found by calculating f prime of 2, which gives us the answer on the second line. Previously, we derived that when n is an integer, whether positive or negative, the derivative of the function x to the power of n is n times x to the power of n minus 1, as shown on the second line of the screen. The mnemonic rule for this is bring the exponent down and then decrease the exponent by 1. What we are going to discuss here is that when the exponent is a rational number, q over p, the derivative of the function x to the power of q over p will still follow the rule. Bring the exponent down and then decrease the exponent by 1. That is, q over p times x to the power of q over p minus 1, as shown on the last line of the screen. We will use the implicit differentiation method to prove this as follows. Let y equal x to the power of q over p, where p and q are non-zero integers. Therefore, we can obtain y to the power of p equals x to the power of q, as shown on the first line of the screen. According to the implicit differentiation method, we will differentiate both sides of the equation with respect to x, as shown on the third line of the screen, where the left side of the equation is obtained by applying the chain rule. The proof process is demonstrated on the last line. Both sides of the first equals sign on the last line are the expressions we want to differentiate, and the right side of the second equals sign is obtained by solving for dy dx from the mathematical expression on the third line. After a simple algebraic manipulation, we arrive at the final expression, which is exactly our mnemonic rule. Bring the exponent down, and then decrease the exponent by 1. This screen shows a few simple examples, which should be easy to understand. This example requires us to differentiate this function on the screen. First, convert the square root to the power of 1/2, and then apply the chain rule to obtain the mathematical expression on the first line. Next, by applying the quotient rule, we can get the mathematical expression on the second line. After a simple algebraic manipulation, we arrive at the final answer on the third line. Here, we would also like to emphasize that x must be greater than 0. This screen describes the mean-value theorem for derivatives. As shown on the screen, suppose that the function f is differentiable on the open interval from a to b and continuous at the endpoints a and b. Since differentiability implies continuity, we can also say that the function f is continuous on the closed interval from a to b. The mean-value theorem states that there exists at least one point C in the open interval between a and b such that the mathematical expression on the fourth line of the screen is satisfied. The geometric meaning of the mean-value theorem can be explained as follows. The left side of the equals sign is f prime of c, which represents the slope of the tangent line passing through the point c, f of c. The fraction on the right side of the equals sign represents the slope of the line passing through the 2 points a, f of a, and b, f of b. These two slopes are equal, which means that this line is parallel to the tangent line. Of course, this line is also the secant line passing through these 2 points, a, f of a, and b, f of b. Therefore, the mean-value theorem states that given a secant line passing through the 2 points, a, f of a, and b, f of b, there must exist a point C in the open interval between a and b such that the tangent line passing through the point c, f of c, is parallel to the secant line. To remember the formula for the mean-value theorem, the mnemonic rule is the slope of the secant line equals the slope of the tangent line. Using this mnemonic rule makes it easy to write down the formula for the mean-value theorem. The mean-value theorem is frequently used to help prove other important mathematical theorems, and you will see it often in the future. This theorem assumes that the function f is differentiable on the open interval from a to b and continuous at the endpoints a and b. If the function values at the endpoints are equal, that is, f of a equals f of b, then there must exist a point C in the open interval between a and b such that the derivative of the function f at point C is 0. In other words, the slope of the tangent line passing through the point C, f of c, is 0. This also indicates that this tangent line is parallel to the x-axis. Its geometric meaning can be explained as follows. Consider the graph of this continuous function. If we start drawing from the endpoint A, the graph can either move upward or downward. Let us first assume the graph gradually goes upward and then returns to the endpoint B. It must start bending downward at some point C in between for the function values at the endpoints to be equal. At this moment, the tangent line at point C will be parallel to the x-axis, meaning the slope of the tangent line is 0. By the same token, if the graph gradually goes downward and then returns to the endpoint B, it must start bending upward at some point C in between for the function values at the endpoints to be equal. At this moment, the tangent line at point C will likewise be parallel to the x-axis, meaning the slope of the tangent line is 0. This is known as Rolle's theorem, and it is also used to help prove other mathematical theorems.